And so we come back to where we left off at the previous in the previous video. And now we have our circle. The circle on the graphing calculator, though, is really made up of two explicitly defined functions: square root of 1 minus x squared and negative square root of 1 minus x squared. But that's a little difficult for us to work with all the time, and sometimes we can't always even solve for y in a particular expression. Now, one of the great things about Wolfram Alpha is that we can actually type in the uh, implicit definition of the function. Again, I use the word function here loosely. The circle is not a function as we've learned a function, but we're still going to call it an implicitly defined function. So we have x to the second plus y to the second equals 1. And if we scroll down, you'll see that you get a graph of a circle. Again, this is the same exact graph that we have on our other screen. We can put the function in implicitly, and we're able to find that Wolfram Alpha is going to graph it for us without any problem. Okay, so we come back to where we were. Now, what you should notice about this particular graph is that it's a circle. It's smooth. The curve is smooth all the way around, even though it's not a function in our traditional sense of a function because it fails the vertical line test. But that's okay. With calculus, what we're really interested in is this curve differentiable? Is it smooth? And if it's smooth, can we find the tangent to the curve at any point? Can we find tangent lines? Can we find the slope of the tangent line, etc.? So that's what we're really interested in here. And with this particular curve, we can do this even without calculus. So let's take a look for a second. So let's say we have some point x comma y that happens to lie on that circle. It has an x coordinate, it has a y coordinate. And we're interested in finding the slope of the tangent line to the curve at that particular point. Well, because this is a circle, we can do a few things. First of all, we can draw a radius from the center out to that point, and the geometry of this tells us that that line, that radius, is what we have been calling, or what we called in the previous example or a previous test that we worked on, a normal line. It is perpendicular to the tangent line at the point of tangency. And we do know a few things about normal lines and tangent lines. First of all, we know that they're perpendicular to each other. Normal line is perpendicular to the tangent line. So if we knew the slope of the tangent line, we would take its reciprocal and its opposite, and we would find the slope of the normal line. And we could find the slope of the normal line, and take its negative reciprocal, and we would also have the slope of the tangent line. So let's say that I was interested in finding the slope of that normal line. Well, the slope of the normal line, the slope of any line, is rise over run. And the rise in this case is just the y value, and the run is just the x value. So if we were looking for the slope of that normal line there, of that radius to the circumference of the circle, then it would just be y over x. And the slope of the tangent line then is just going to be the negative and reciprocal of the slope of the normal line, which is going to be negative x over y. And that would hold for any point along the circle. It would always be negative x over y, and we could always find it using the same exact method that we just found here. So what we would like to do, though, is to take this a step further and to see how we can go about finding the derivative using a new method.